For the given problem, first of all note that if the situation would have been like this, then we could say that as the mass on both the sides is equal and both move by the same amount in the opposite directions, so the center of mass of the system will remain stationary. We could also say that in this case, the tension in the thread will be equal to the weight on either side. So the force exerted by the clamp will be equal to the total weight on both the sides. Therefore, the net force on the system is equal to 0. And thus, the center of mass should remain unaltered. But in this case, there is a relative motion between these masses. In order to rise up, this object must push down with a force greater than its own weight. So in this process, tension in the thread will momentarily exceed the weight of both the objects. Due to this, the force exerted by the clamp will momentarily exceed the total weight of the system. So here, the net force on the system will not be 0. And thus, the position of center of mass will change. Let us say that in this process, this block moves up by an amount y. So the ladder goes down by the same amount as this object climbs up a distance L with respect to the ladder. So its net displacement is equal to L minus y. Now, taking this direction to be positive and using the equation of center of mass, we can say that the total mass of the system into the displacement of center of mass should be equal to the sum of these terms. Solving this equation, we get the displacement of the center of mass of the system. Due to this displacement of center of mass, the potential energy of a system has increased by the amount equal to the total mass of the system into g into this displacement, which comes out to be equal to mgl. This increase in potential energy can result only from the work done by this object, as the work done by tension on either side will cancel out each other. Here you must note that it would be difficult to find the value of y if we work with the conventional set of x's and use proper signs for displacements. However, if we use our unconventional x's, as discussed in the chapter on forces, then the situation can be considered to be similar to this. Here we can say that as there is no external force in the direction of motion, so the center of mass of the system in this sense will remain stationary. So if the block and the ladder move by a distance y, then this object moves a distance L minus y. And we can say that m plus m into y plus m into y should be equal to m into L minus y. That is, y should be equal to ml upon 2 into m plus m. This means that this block rises by the amount equal to the displacement of the center of mass of the system. But if the displacement of the center of mass of the system is equal to the displacement of this block, this means that the displacement of center of mass of this system should also be equal to this height. Displacement of center of mass of this system will be equal to minus my plus m into L minus y upon the total mass of this system. Using this value of y, we can see that indeed the displacement of center of mass of this system is also equal to y. This is expected because the situation is symmetrical. So if the center of mass of one side has gone up by some distance, then the center of mass of the other side should also go up by the same amount. Now with this information, we could have found the value of y using a conventional system also. Here if we write the equation of center of mass for this system, then we can say that m into minus y plus m into L minus y should be equal to m plus m into y. Solving this equation, we again get the same value of y.